So chapter number 8 is our last chapter that we are going to discuss, and this deals with filters and specifically active filters. You guys have worked on filters before in circuit analysis, of course. We have worked on filters in signal processing, digital filters. Now we are going to look at active filters. So again, many of you are familiar with what filters are. They are frequency selective circuits. They select the output of the circuit over a band of frequencies. And outside that band of frequencies, the output is supposed to be 0. Ideally, this is the response of the filter against frequency. Ideally, of course, that everything is passed over the pass band. This is your pass band. Everything is passed over the pass band, and everything is stopped when your pass band is outside the pass band, rather. So pass band is where your response is going to exist, and stop band is where everything is going to be stopped and your output is going to be 0. So that's how how filters work. They extract frequencies or the output based on the frequency range. Like out of this frequency range, I'm going to take the output of the circuit. You have low pass, of course, that low band of frequencies, everything is passed. High pass, high band of frequencies, everything is passed. And of course, you have band pass and band stop, these 4 filters. FC represent the cutoff frequency. That is the frequency at which everything is going to be cut off. So after that, there's going to be nothing. And before that, there's going to be everything. And band pass, it has 2 cutoff frequencies. You have the lower cutoff frequency and the upper cutoff frequency. And the middle frequency is called the resonant frequency, which is generally represented by F0, which you see over here. So this is FC1 and FC2, or FCL, FC high, FCL and FCH. And likewise, a stop band has stop band cutoff frequency, low side, and cutoff frequency, upper side. And between these 2 cutoff frequency, you have the stop band. It is impossible to pretty much create ideal filters. And there was a reason that I discussed with you since many of yes. Oh, okay. Let's see this. Did you get it? Okay. Okay, so maybe last week or this week sometime, I think maybe this week, I discussed with you, some of you who are in signal processing class, I guess. I don't know which class, maybe in power systems. I forgot anyways. I discussed with you why, no, I think it was signal processing, why it is not possible to create an ideal filter, low pass, high pass, whatever, let's say low pass, ideal low pass filter, even in theory. What was the reason? Anybody remember that reason that I discussed with you? It has to do something with the sinc function, if you remember. Okay. Nobody remember that? Okay. All right. Let's just to recapture. Ideal low pass filter, the response of which is this. For this frequency response, if you go to time domain, you are going to get a sinc function. That is sine of t over t, something like that. And the sinc function is a function which is symmetric about y-axis. And if you plot it against time, then it's going to look like this. So what did I discuss about that? Anybody remember that I discussed something specifically as why cannot you have an ideal response of a filter based on the discussion of that sinc function in time domain, whether the time domain is digital domain or analog domain. Anybody remember that? No, it has to do with the time function is expanding on the negative side. That is, the time function is starting before t is equal to 0. That's the problem with the response. If you convert this response using your inverse Fourier transform into time domain, the sinc function is the response, and sinc function starts before t is equal to 0, which is not possible basically. So even theoretically, it is impossible to create an ideal low-pass filter. So of course, we have practical low-pass filters, but we can go as close as possible to the ideal response if we keep increasing the size of the filter, whether it's an analog filter or digital filter, and we can get a really good filter with sharp slope from the pass band to the stop band. Anyways, so that's what I put down, this fourth bullet point. In general, an ideal filter response is not achievable, but one can design higher order filters to get close to the ideal response, and it is not achievable because of the response being a sinc function in time domain. Now, the practical filters, again, they don't have just two bands, pass band and a stop band, but you also have a transition band. That is when the pass band is transitioning into the stop band. So that band of frequencies is the transition band. So you have the pass band, let's say FC, and then you have the stop band, F stop. And between FC and F stop, you have the transition band. Now, the sharper the transition band it is going to be, the closer the response is going to look like an ideal response. And if the transition band is wide, then it's not going to be as close to ideal response as we want it to be. And it will also let other frequencies pass through the filter that are not required, because when it is going down and if this slope is not very sharp, then some of the values of the input signal, they're also going to be transmitted to the output, although we may not want those values outside the cutoff frequency. So we want this transient response, transient band, to be as steep as possible. So this is pass band, stop band, and transition band, just the discussion of the three bands. Two categories of analog filters. One is active that we are discussing, and one is passive that you discussed in circuit analysis. From the name, you can see active filters are the one that employ active components. Active components are the components that require some external power supply to be excited. For example, operational amplifier. You need biasing voltage for the operational amplifier to work. So you need some extra power supply. That's an active element. On the other hand, passive element, they don't really need any extra power supply. If you have an input source, you can get an output response. For example, your capacitors, your resistors, your inductor, you don't really need to connect them with extra power supply. You just have a circuit, you connect an input signal, and then you can get an output signal. And at different frequencies, of course, response of the capacitor and inductor is going to change because of the impedance of those. And based on that impedance response, your frequency response of those circuits is going to change. So passive filter do not employ any component that requires an external power supply. An active filter do employ those components, for example, operational amplifier, and that's why we are discussing active amplifier in this course, because they employ operational amplifiers. So that's the main difference between active and passive filters. The other difference between active and passive filter is active filter can also provide gain during their pass band. Passive filters cannot provide gain. They can provide the frequency selectivity, but they cannot provide gain in their pass band. Active filters can provide both. They provide frequency selectivity. You can select the band of frequencies, And over that band of frequencies that you are selecting, you can also have gain more than 1. That is, your output can be larger than the input over that band, which is the pass band. Passive filter is not possible. Passive filter, the maximum output that you are going to get is equal to the input value over the pass band. So their gain in the pass band is always 1, or maximum gain in the pass band is 1. It can be lower than 1 as well, because the cutoff frequency goes. What is the gain at cutoff frequency in general? Anyone? 70% of the peak value of the input, right? So the pass band goes from the maximum value of the input at DC until the cutoff frequency at which your output is 70.7% of the peak value, which happens at the DC voltage. That is frequency 0. So active filter and passive filter, active can provide gain as well as frequency selectivity. Passive cannot provide gain. Only they can provide frequency selectivity. The filter that we are going to discuss, there are many active filters, of course. The one that we are going to discuss are the Butterworth filters. And we are going to discuss 2 types, low pass and high pass, and we're going to design them. You're going to do the lab number 7, where you're going to design them, and you're going to see which, and in the lab, I think it's the 5th or 7th order filter that I'm asking you to design. I forgot which one. But you're going to look at the response of the filter, and you're going to design it first, and we're going to look at the response of the filter. When you're designing a filter, generally we use a normalized model, so a pre-existing filter we use. So this is our base filter, which is called the normalized filter. And then we change 2 things. We change, of course, the cutoff frequency, because our cutoff frequency requirement can be any frequency. Normalized filters may have a specific value of the cutoff frequency. So we have to change the important frequencies of the filter. That's called frequency scaling. Frequency scaling. And then normalized design, they have a specific value of components, whether they are resistors. The one that we are going to use are resistors and capacitors, and of course operational amplifier. So you have specific values of resistors and capacitor in the normalized design, in the base design, let's call base design or reference design. And many times those values either we don't have, or they're not going to work for us because those values are either too small or too large. So if we go to our kit, we may not be able to find those values, which means that we have to choose the values that we have. So we have to change the values of the standard components. Let's say if you have 1 ohm in the standard, it's like, this is too small. 1 ohm is going to produce a lot of noise, or we don't have 1 ohm. Then we have to change that 1 ohm into, let's say, 10 kilo ohm, because that's the one we have. So to do that, we have to perform impedance scaling. So there are 2 operations that you will have to do when you're designing a filter based on the normalized design or the reference design. You're going to do the frequency scaling, as well as you are going to do the impedance scaling. And once you do both of this, then you get the final design with the cutoff frequencies that you want and the component values that you have in your kit. That's the idea that we are going to employ as far as the design of active filters are concerned. So for the normalized filter or reference filter, you're going to have normalized cutoff frequency, which will be given to you. And you are going to change that normalized cutoff frequency into the cutoff frequency that you want from your system. Likewise, you have the resistors and capacitors, standard values, and you are going to change those values into the values that are more comfortable for you to use, or you have those values. Generally, as I said, we've been doing that. It's better to choose the capacitor values because capacitors values are selected values that we have in our kits. Resistors, we can have many values. Generally, we choose capacitor values and then we calculate the resistor values for our design. 2 things we have to do: frequency scaling and impedance scaling. Frequency scaling is done using the frequency scaling factor. What is the frequency scaling factor? It is the ratio between your required frequency and the normalized frequency of the system. So this is your required frequency. Let's say you wanna have a 10 kilohertz cutoff frequency, and the base filter that you're using, it has 100 ohms, 100 hertz cutoff frequency. So KF, first you're going to calculate as the ratio between 10 kilohertz or equivalent radian per second and 100 hertz equivalent radian per second. And that is going to give you the frequency scaling factor. So that's the first thing. So that is your required frequency. And this is the frequency of the normalized filter. And the ratio of 2 is going to give you the frequency scaling factor K. So omega r is the desired angular frequency, and omega r bar is the normalized frequency of the filter. So when you calculate Kf, then you're going to divide all the capacitors or all the resistors by the value of Kf to calculate the new values of capacitors or resistor. You have to do only one of them. Either you calculate the capacitors or resistors. See, that's why this is or. You don't have to do and. You don't have to calculate the values of both resistors and capacitors. You have to calculate only one item, either it's capacitor or resistor. So the new value of capacitor you can calculate as the old value divided by Kf, or the new value of resistor you can calculate old value of resistor over Kf. And that is going to provide you the desired frequency by the changing the capacitor, which is preferred, or changing the resistor using Kf. So again, one of them. If you're satisfied with the values, then the filter has been designed. So you don't have to do anything else. If you see that, okay, my new values are good to go, then you have designed your filter. You don't have to do impedance scaling. But many times, that's not the case. You do have to do impedance scaling, because the values that you're going to get, either for a capacitor or resistor, in the normalized circuit, after you apply the frequency scaling, those values might not be very good values to create a circuit. They may be very small, very large. You may not have them in your kit, whatnot. So impedance scaling, pretty much 100%, you have to perform impedance scaling to get the new values. But the first step is your frequency scaling. When you do impedance scaling to choose the values or to calculate the values that are more suitable in the circuit, the first thing that you do is to calculate the impedance scaling factor, which is represented by Kr. And that's the ratio between the desired value, desired impedance, and the current impedance that you have in the circuit. So Kr, and remember we are talking about impedance or resistance. So for capacitor, Kr is the targeted value of the capacitor impedance and the old value of the capacitor impedance. And you have to do for both, basically, for the resistors and the capacitor. And the Kr, or you have to calculate from one, and then you're going to change both values though by multiplying it or dividing it. Or Kr is R new over R old. So it's the same thing as Kf. Kf is also the new frequency over the old frequency. And Kr is also the new value of the impedance or resistance over the old value of impedance on the resistor. Old value means in the last step that you had. And since the reactance is 1 over j omega c, so that's going to be 1 over j omega c new 1 over j omega c new over 1 over j omega c old, then that's going to give you C old over C new, which is this. So Kr can be calculated if in terms of the capacitor as the old value of the capacitor over the new value of the capacitor, or the new value of the resistor over old value of the resistor. But in general, it's easier for me just to remember for both Kf and Kr, we are looking for the new value on top, whether it is reactance or resistance, and the old value at the bottom, whether it's frequency, resistance, or reactance. So the ratio between the new and the old. It's very easy for me to remember instead of remembering this ratio, R new over R old or C old over C new. I think it's much easier is always go for new on top and old at the bottom, whether it's the resistance or reactance or frequency, new frequency over old frequency. Okay, once you get the value of the impedance factor, multiply all resistors and divide all capacitors by that value to get the new values of capacitors and resistors. So multiply all resistors and divide all the capacitors. If the new values that you calculated are still not good, then impedance factor can be recalculated using some other component, and new values of component can be obtained using this new value of Kr. You're going to see when we do the examples. The new values of component that you obtain using the impedance scaling factor, it does not disturb the frequency of the circuit that you set using the frequency scaling stage. If an amplifier has multiple stages, then you can choose the new value of Kr for each stage if you want, or you can keep the same value of Kr and then calculate the new values of capacitor and resistor for each stage separately. So this is basically two things that we are going to be doing from this point on in order to design filters: scaling of the frequency and scaling of the impedance. Okay, so this is a passive filter. It only has a capacitor and a resistor. It's a low pass filter. Why do we say it's a low pass filter? Anyone? What is the reason that we say it's a low pass filter? Well, everyone should know this answer. Say it again. Yeah, that's what the function of low pass filter is going to. But why? If I give you this circuit, I ask you it's a low pass filter or high pass filter, then how are you going to explain that? No, this is a low pass filter or this is a high pass filter? Yes, Rahul. Okay, that's from your memory though. But what will be the justification? How are you going to justify that this is a low pass filter? That it is letting low frequencies pass? Someone should answer this, except Yunus. Yes. I'm sorry? I don't think I follow you. I'm not sure what you're trying to say. Well, there's always cutoff frequency for high pass and low pass and band pass, right? But that's not the point. I'm looking for a justification that this is a circuit. It's written here low pass filter. But why did I write it's a low pass filter? If I don't write it and I ask you identify the filter, Rahul said, well, the capacitor position is this, it's a low pass filter. Okay, I get that, but what is the justification? It's not just the position. The position is playing a role in making this filter a low pass filter, right? What is that? That brings the justification. That what role that capacitor is playing when it is connected at that location, or resistor is that location. No, it has nothing to do with noise. That's the answer. That's the answer, exactly. Very good. Reactance of the capacitor, 1 over omega c, right? So omega, when you have low frequencies, omega is 0, start with DC, omega is 0, Reactance of the capacitor is infinity, 1 over 0, almost very high. That means that it's going to be an open circuit. So whatever input is coming in, that's going to be going out. No current flowing through the circuit, no drop in resistor. As omega starts increasing, reactance starts going down, 1 over omega c. When omega becomes extremely large, reactance becomes extremely small. That means, let's say omega becomes infinity, reactance becomes what? Short. So the output becomes 0 because it's going to be parallel to the short circuit. So the reactance of the capacitor, in this case, you can pretty much determine if it's a low pass filter or high pass filter based on the reactance. Same thing with the inductor. Instead of capacitor, if you use inductor, reactance of that inductor, you can determine what frequencies that reactance is high and at what frequencies that reactance is low. And based on that, you can determine if the output is going to exist at those frequencies or it is going to be 0 at that frequencies. So in this case, output is going to exist at low frequencies because capacitor value is going to be starting from open circuit and then it starts going down. So you will still have some output until it becomes very small, that most of the voltage is going to be dropped in your resistor and very small voltage is going to be dropped in the capacitor because they're connected in series in this case, of course. So that's the justification. That's what you're going to write down if or explain if somebody is going to ask that why it is a low pass filter. It's because of the impedance of the capacitor. So normalized low pass filter is given. Normalized values of the resistor is 1 ohm. Normalized value of the capacitor is 1 farad. And from let's write down who's going to tell me what will be, this is V input and this is V output. What will be the output in terms of the input? Who's going to tell me? One second. Yes, what is the output expression in terms of the input voltage? XC over R plus XC times the input voltage. Very good. XC, of course, is the reactance of this capacitor. So the transfer function or the gain of the amplifier, which is the output over input, which is the gain, or in general we call it the transfer function, is XC over R plus XC. And if we put the value of XC, then it's going to be 1 over j omega c over R plus 1 over j omega c. So the transfer function is simply, not the magnitude, but just the transfer function is simply 1 over 1 plus j omega Rc. And this is the first order filter. So we can write this down as 1 over 1 plus j omega over omega c, where omega c is the cutoff frequency, and that can be given by 1 over Rc. So at the cutoff frequency, the magnitude of this, what will be the magnitude expression for this, guys? Anyone? We can write the magnitude expression for this. Yes, Andy, you tell me, what is the magnitude expression for this? Magnitude response expression. We did that in last chapter, or chapter number what? 5, chapter number 5. Yes. It's a complex number, right? What is the magnitude expression for this? It's a complex number. You cannot calculate the magnitude expression for a complex number. Then what will be the magnitude expression? You have a small mistake there. Who can correct that mistake? Ronaldo? Huh? Take out the J, okay. All right. So 1 over square root of 1 square is 1 plus omega RC square without J. So then when there is no J in there. It's the real square plus magnitude of the imaginary square. Okay, or simply 1 over square root of 1 plus omega over omega C square. So again, if omega is equal to omega c, denominator is going to be a square root of 2, and 1 over a square root of 2 is 0.7071, which tells you that at omega is equal to omega c, the magnitude is going to be 70.7% of the peak value. In this case, peak value is going to be 1 because at omega is equal to 0, this is going to be 0, and the magnitude is going to be 1. So the peak value in this case is 1, that is input is equal to the output at DC. Omega is equal to 0 is DC. And then from that point on, as you start increasing the frequency, the output starts going down. And the cutoff frequency at cutoff frequency is going to be 0.7071. 0.7071 times the magnitude of the input, basically, is the output. All right, who is going to tell me now, again, just so that it is fresh in your mind, what is the phase response expression for this? Yes. Okay, so what Chris said is exactly right. Anyone else can tell me what is the phase response expression? Because I'm pretty sure people in the back, they did not hear what Chris said. So anyone from the back can say it aloud so everyone can hear. What is the phase response expression for this? Yes, Earl, what do you think? Phase response expression. Okay. Look at the expression and then you know what it's going to be. You look at the expression and then apply what you're saying. Okay, that's correct. Minus? No, you're thinking about phase lag and phase lead circuit and applying that to every situation. that's not how it is. That's a phase lag and phase lead circuit. This is not phase lag or phase lead. All right, who's going to tell Mike? What do you think is going to be the phase response expression? Say it again. Okay, there's something missing in there. No, what 90 is coming from? 90. There's no J in the denominator. All right, Rudley, what do you say? Then say to everyone. What? Okay, go ahead. That's okay. Just what you're telling him, just tell it to everyone. What you're saying. Phase lag. Well, this is if you apply phase lag, phase lead to every circuit, then you can say goodbye to your grade. Okay, in general, again, I know how many times I say the same thing, and again, any complex number that you have written in the rectangular form, how do you calculate phase of that? Who's going to tell me? Yes, you wrote. No. Any complex number that you have, how do you? Yeah. Okay, y over x. So imaginary over real. Arc tangent of imaginary. That's how you calculate the phase of a complex number. If it's given in fraction, what do you do? And again, but I'm going to say the same thing. this time, and next time I'm going to ask, then you're not going to tell me, because you guys don't write down. You guys need to write down important things so you can revisit. All right, how if it is in fraction, complex number, like this number is in fraction, given in fraction, then how do you calculate the phase if the complex number is given in fraction? I know you know that. I'm trying to ask the people who, yes, phase of the top one minus phase of the denominator, right? So apply that to this and tell me now what will be the phase. Edwin, what do you say? Negative arc tangent of omega RC, okay. And how did you calculate that? What about the numerator? I'm not asking you to look at ChatGPT and then give me the answer. Come on, just explain it to me. I can look at ChatGPT and anybody can look at that and then explain it. Don't look at ChatGPT. Answer me what will be the phase. How do you calculate the phase? We just discussed. Do you calculate the phase with the phase of the numerator minus phase of the denominator? What is the phase of the numerator? This question is that hard? I mean, come on. Oh boy. Yes, Caitlin, what's the phase of the numerator? 1. Phase of the numerator is 1. Okay. Is that correct? Is the phase of the numerator 1? No. Okay, Diego, what is the phase of the numerator? 0. Why? There's what? Okay, so where does that point exist? In general, you determine the phase based on the location of the point on the complex plane. Where does that point located? It's located. No, its origin is 0. You have 4 axes of the complex plane. You have 4 axes, right? What are those 4 axes? Huh? You have positive x, negative x, which represent what? Real number. And then you have positive y and negative y, which represent imaginary number. So where is that point going to be located? On the real axis. What will be the phase of any point located on the real axis? 0. It's going to be 0, right? So the phase of the numerator is 0. Okay. Now you have to subtract phase of the denominator. And now what is going to be the phase of the denominator? Tangent inverse of what? Omega RC over 1 or omega RC. Oh man, why it's so hard? Guys, you have like all the information in the palm of your hand, and I still don't understand why the level of knowledge is going down. I don't get it. Instead of looking at ChatGPT just to give answer, it's better if you look at ChatGPT to understand and learn. That's going to help. It's not going to help if I'm asking a question and then you just look at ChatGPT just to answer my question, and next time I'm going to ask the same question and then you won't be able to answer it. You have all these resources available, use them to learn. And come on, how hard it is. When you're doing your senior design, everyone is going to ChatGPT and trying to see how to do this thing, that thing. That's perfectly fine because you're trying to learn. But the same thing you can apply, for your courses. Learn, use those resources. I mean, you have a wealth of resources available. Anyways, so it's going to be tangent inverse of omega RC, or in general, negative arctan of omega over omega C. Okay. Now our goal is different. Our goal is what? Our goal is that we need to have the cutoff frequency of 1 kilohertz and capacitor value should be 0.01 microfarad. That's our goal. So the normalized capacitor value is 1 farad. We got to change that value to 0.01 microfarad. And we want to make sure that our cutoff frequency is 1 kilohertz. Now, the cutoff frequency, omega c for this is what? 1 over 1 times 1. So 1 radian per second. That's the cutoff frequency of the normalized field. We got to change that 1 radian per second into the equivalent of 1 kilohertz. So 2 pi times 1 kilohertz, 2000 pi. And then once we change that, we also want to make sure that our capacitor value is 0.01 microfarad, and we have to calculate a new resistor value. So we have to perform first the frequency scaling. Frequency scaling. Frequency scaling is the new value over the normalized value or the old value of the cutoff frequency. Let's write down cutoff frequency is 10 of omega r, cutoff frequency. The new value of the cutoff frequency is 2 pi times 1000, so 2000 pi radian per second. And the old value is simply 1 radian per second. So kf is simply 2000 pi. Does kf has a unit? Does kf have a unit or not? No, because it's a ratio between two same quantities. So it's simply 2000 pi without any unit. Don't put radian per second here. Okay, once you have your kf, what is the next step? You gotta either change the value of the capacitor in the circuit or change the value of the resistor in the circuit using this kf. So let's go ahead and change the value of capacitor. So the new value of the capacitor is the old value over kf, and you can do the same with the, if you want to choose resistor, you can do the same with the resistor. So if I go back again, frequency impedance, so you're gonna have this new value of the capacitor old over kf, or the new value of resistor old over kf. You can choose either capacitor or resistor, one of them only. Make sure don't do both of them, one of them only. So the old value of the capacitor is 1 farad over 2000 pi. Right. Who's going to calculate this? What is the value? $159.1 microfarad. Okay. So now your circuit has the new value of the capacitor that you have, this one, and the old value of the resistor. So this is 1 ohm, and this is 159.1 micro, or input and out. So the cutoff frequency for this one, we calculated already, but the cutoff frequency is going to be omega cutoff is 1 over RC nu, and that's going to be 1 over 159.1 micro, which is going to give you 2000 pi, which means that the cutoff frequency you have now successfully set to 1000 hertz. That's what we have to do, right? 1 kilohertz. 1 kilohertz here. So the cutoff frequency is set. So make sure you have to choose only one, you have to change only one, either capacitor or resistor, because if you change both of them, then their combination is not going to give you the cutoff frequency. All right, 159.1 microfarad, that's fine, but that's not our goal. Our goal is that it has to be 0.01 microfarad. So now we have to do the impedance scaling. And of course, R value is too small, 1. We got to change that value. So impedance scaling, KR, impedance scaling, since we know the old value of the capacitor, we're gonna, I mean the new value of the capacitor, we're gonna use that new value in order to calculate the impedance scaling factor. Now once again, that is X new over X old, or R new over R old. And X new over X old means C old over C new. So this is C old. And remember, this old is not the same as this old. So this old is the C new, whatever you had in the last step. So this C new that you have calculated, 159.1 microfarad, this is now the current value of your capacitor in the circuit. So you are changing now these values. You're not changing the original values. Now this is your circuit. So you are changing these. So perhaps we can change, we can use some other variable just to make sure that you guys are not confused. So it's C new over C old, and let's see. Maybe we should use C new prime here. C new prime. That might be a better way to do it. So this is C new prime. That's a C new prime. Let's see. So that's going to be C new prime, which is now C old, over the final value, which is a C new. And again, we are using this KR is equal to C old over C new. This old is now C new prime for us. So C new prime is 159.1 microfarad. And we want the last value, the new value, to be 0.01 microfarad. Right? 0.01 microfarad. So my impedance scaling factor is simply going to be, microfarad will cancel out, and that's going to be 15910, right? 15910. That's going to be my impedance scaling factor. Again, there's no units because it's the ratio between the two same quantities. Now, impedance scaling factor has to be multiplied by all the values of resistor to get the last value or the new value of resistors, and the value of capacitors, they have to be divided by impedance scaling factor. We already know the value of capacitor, the new one, of course, it is 0.01 microfarad. So if you divide 159.1 by 15910, you're going to get 0.01 microfarad. That's our target anyways. So all you have to do is to change the value of resistor. So multiply all resistor, in this case one resistor, by KR, and divide all capacitors by. So when you multiply that, the new resistor value is going to be 15.91 kilo ohms, 15.91 kilo ohms, and the capacitor value, of course, is given to us, which we use to calculate KR, so that's not going to change. 0.01 micro, which will be 10 nanofarad. And these will be our final values. Well, one value was given to us, but this is going to be, resistor value is going to be the final value. The impedance of the circuit is going to be the same. If you take the original circuit, calculate the impedance at the cutoff frequency, which was 1 radian per second. That's going to be the same impedance as the new circuit that has the cutoff frequency of 1 kilohertz or 2000 pi radian per second. So the impedance at the cutoff frequency is not going to change. And you can do that if you want. Okay. Any question about this? Anything that is not clear, because this is the process over and over again that you're going to be repeating. Yes. It's impedance scaling is KR. KR represent resistance basically. KF is the frequency. Let's go ahead and take a break, and after the break, we are going to start the active Butterworth, which is the goal of this chapter. Okay, guys. So active Butterworth, low pass and high pass filter. Order of the filter represent number of reactive elements. So if you are creating a filter and if you have two capacitors in general, it's a second order filter, or two inductors, or one capacitor or one inductor. Those are second order filters or second order circuit, like you did in circuit analysis, RLC circuit, RC circuit, RL circuit. RL and RC circuits are the first order circuit because their relationship can be represented by a first order differential equation. And RLC circuit, if you remember, the equation that you wrote for RLC circuit was a second order differential equation. And that's why they are called second order systems or second order filters. So the number of reactive elements determine the order of the filter. The higher the number of reactive element, the more complicated the filter is going to get, but the response is going to be better in general. So nth order active Butterworth low pass filter, the magnitude response is given by this. So it's a first order response, but again, this n represent what is the order of the filter. And in decibel, of course, when you doing the magnitude response, it's 20 log 10 of this, which becomes negative 10 log 10 of 1 plus f over fc2n, because the square root, of course, is going to, if I simplify this thing, then it's going to be 20 log the base 10 of 1 minus 20 log to the base 10 of 1 plus f over fc power 2n, and this is a square root, so that is going to be power half the whole. So this half is going to, of course, 20 log 10, 1 is 0, and this half is going to come here, it's going to become negative 10. So that's negative 10 log 10 of 1 plus f over fc to the power 2n. This is the magnitude response in decibel for Butterworth filter of any order n. Cutoff frequency fc, as we discussed, is the frequency at which the magnitude response goes down to 70.7% of the peak value, also called 3 decibel frequency, because the power at the cutoff frequency is half as compared to the peak power, and half in the decibel scale is 3 decibel, negative 3 decibel. Oh, just repeated, I guess. Magnitude frequency response, we just discussed that. Decibel, we discussed that. Oh, there's a high pass filter, not low pass. So for high pass filter and low pass filter, it's pretty similar. Low pass filter is F over FC, and high pass filter is FC over F. So it's similar, basically. It's just the opposite as far as the ratio is concerned. Cutoff frequency is still the same, that is 70.7%, although it's a high pass. And when you plot curves from 8.4 and 8.6, that is, you plot the magnitude response from 8.4 for the low pass filter, or magnitude response from 8.6, assuming FC over F or F over FC is a variable X, whatever variable you want to call it, then you are going to get something like this. And this is for multiple values of n. It's hard to see, but I'm going from n is equal to, let's see, n is equal to 1 all the way up to n is equal to 10. And then the cutoff frequency is where the response is 0.707. X-axis here is normalized frequency. So just a variable x, that x is F over FC for low pass and FC over F for the high pass filter. So basically what you're plotting over here is 1 over square root of 1 plus x to the power 2n, and then x is going to be FC over F for high pass and F over FC for low pass filter. And you can plot the same in the decibel scale from the equations that we discussed. And in the decibel scale, the cutoff frequency is going to be -3 decibel is when the cutoff frequency is going to be. We are going to be using these, and I will advise you to just plot in MATLAB and then keep that plot or just generate it. All we are doing is, once again, we're plotting this equation and just use x for F over FC or FC over x, and then just x is your x-axis and change the value of n and generate multiple plots. I'm going from 1 to 10. I think in the book, if you do have the book, in the book they're going from 1 to 7, if I remember correctly. I just went from 1 to 10. Yes? The curve that we see there are the low pass. It's like this is basically it's the magnitude response of 1 over 1 plus square root of x. That's the magnitude response, right? Yes, F over FC or FC over F, whatever you are saying. So when we use these plots to create the filter, you will see how we are going to interpret this for both. All you need is this plot for 1 over 1 plus x to the power 2n. That's all you need. But when we interpret this for the high pass and low pass, we're still going to be using the same, but you will see how we are going to interpret this for high pass and low pass in a little. But we're going to be using this for the design. Using this or this, I forgot which one, but you will see in a minute, either decibel or the linear. Okay, example. A low pass Butterworth filter is desired to have the following frequency specification: relative attenuation less than 3 decibel for frequency less than or equal to 800 hertz, and relative attenuation greater or equal to 23 decibel for frequency greater than equal to 2 kilohertz. Determine order of the filter. Okay, attenuation, remember, is 1 over gain, is the reciprocal of gain. In decibel, attenuation is negative the value of gain. When you put 20 log 10 of 1 over gain, 20 log 10 of 1 is 0, minus 20 log 10 of gain. So it's going to be negative gain in decibel. So attenuation is inverse of gain, attenuation 1 over gain in the logarithmic scale. 20 log 10 is negative gain in decibel. So a gain of 10 decibel means attenuation of negative 10 decibel, and a gain of negative 10 decibel means attenuation of 10 decibel. For condition 1, relative attenuation is less or equal to 3 decibel for frequency less or equal to 800 hertz. What does that mean? That the relative gain is greater or equal to negative 3 decibel for this frequency. And that's going to give you the pass band information, and it tells you that the cutoff frequency is about 800 hertz that we are looking for, because negative 3 decibel gain is at the cutoff frequency. So the first one tells you the pass band information. Now, attenuation 23 decibel, greater or equal to 23 decibel means gain is negative 23 decibel, which is mean gain is very small, which means it is way down as far as frequency band is concerned. And the frequency is greater or equal to 2 kilohertz. That gives you the stop band information. So the second condition says relative attenuation is 23, which means that the relative gain is less or equal to negative 3 decibel for f greater or equal to 2000 hertz. This gives the information about the stop band of the filter, which tells us basically where the stop band is starting, about 2000 hertz, and for which the gain can either be negative 23 decibel or less than that, negative 20 decibel, negative 24, negative 25, any value of gain which is either negative 23 or less at 2000 hertz is acceptable according to the condition, which means any attenuation of 23 decibel or more than that is going to be acceptable. And since we are designing a low pass filter, we are going to take f over fc as our normalized frequency, which is x, remember. So we're going to take f over fc, and we're going to calculate the normalized value as far as stop band is concerned, because we know our fc is 800 and our stop band is 2000. So the normalized value is 2.5 f over fc. We will go to the decibel plot of Butterworth filter shown in figure 8.5 and locate the lowest order filter for which the gain is less or equal to 23 decibel at the normalized frequency of 2.5. And as I said, I'll encourage you to plot it in MATLAB because it just makes it easy. So basically we go here because it's given as 23 decibel, and again it's very hard to see. Let me again go and let me increase it from here maybe. So what we are looking at is 2.5 on the x-axis. That's our f over fc ratio, because this is f over fc or fc over f. So this is x. So the value of x that we are looking at is 2.5, which is the ratio between your stop band and the cutoff, 2.5. And that 2.5, 10 to the power 0 is 1, so it's going to be somewhere here between 1 and 10. This is 2, so 2.5 is going to be somewhere over here, let's say. This is somewhere 2.5. Right over here. So we're going to go along this line and we will observe which order is going to have a gain of negative 23 decibel, and we're going to choose the lowest order, not the highest order, because highest is going to become more complicated. We're going to choose the lowest order at which your gain is close to negative 23 decibel, because that's the stop band gain. It can be negative 23 or and more than negative 23, but whichever is closest to it. It cannot be negative 22 because that's going to be higher than negative 23. So according to, again, I did it in MATLAB, but it's hard to look at, how to do it from here. In MATLAB, it's easy. But if you go here, oops, and I put down the values, but if you go up and look at all the values that you have, again, I did it in MATLAB, but it came out to be the order 3, which is this line. That this line was, the gain was negative 23 point something. What I put down? Negative 23.3. And again, if you go to fourth, it's going to be, it will satisfy, but it's going to be higher than 23 decibel or less than negative 23.3 as far as gain is concerned. But the order of the filter is going to increase. That means the complexity of the circuit is going to increase. So you got to choose the one that is the least complex, but satisfy your requirement. So whichever is from the top, because the top one is order 1, and then 2, 3, 4, and the last one is order 10. Whichever from the top is the first one that satisfy your requirement, you're going to choose that. And according to, again, my observation on the MATLAB plot, it is hard to observe it here, but that's why MATLAB plot is important. According to my observation, that was the third one that was giving me the value of negative 23.3 gain. And that's why I chose the order of the filter to be 3. Any question about this? No? All right, let's look at the next example. So in this case, we are doing a high pass. Gain is negative 3 decibel, greater or equal to negative 3 decibel for F 2.5 kilohertz. So we are doing high pass. You have 2.5 kilohertz, and then you have 1.5 kilohertz. Two important frequencies are given, 2.5 and 1.5. So gain is greater or equal to negative 3 decibel for 2.5 kilohertz. That will give you the pass band, F pass. And gain is less or equal to negative 40 decibel for F greater or equal to 1.5 kilohertz. So that's going to produce the stop band. The stop band, let's say 1.5 kilohertz, we need to have a gain of negative 40 or less than that, negative 41, negative 42, or attenuation of 40 or more than that. So this will set the stop band frequency and pass band frequency for us. And again, we have to calculate the normalized frequency X. For the high pass, gain is FC over F. Again, this is X, which is 2.5 over 1.5. Cutoff frequency is 2.5 kilohertz. The stop band frequency is 1.5 kilohertz. And that gave us 1.667 as the value of X. So we are still going to use the same. And we will see what is going to be the order of the filter that will give us negative 40 decibel or less at 1.667. So we go to the same graph, we go and do 1.667 now instead of 2.5. It's going to be somewhere over here between 1 and 2. So let's say 1.667 is this, 1.67. So now we're going to go up and we are going to observe which one is the first line from the top that satisfies the condition for negative 40 decibel or less gain. And for that, I found that 9th order filter was satisfying the condition, which is this line, right, this line somewhere. So the 9th order filter was satisfying the first, that was the first one that was satisfying the condition. So in this case, we are going to choose order of the filter to be order 9. So that's how we are using X only, just to observe that from the same plot, whether it's FC over F or F over FC. All we need is the value of X and the order of the filter, because that's the only thing we are getting from that figure. What is the order of the filter? That's the only thing we are getting. Design of the filter is going to come next, but order of the filter is determined from that graph. All right, once you determine order of the filter, now you have to design the filter, the Butterworth filter. So how are we going to design the Butterworth filter? We have two sections of Butterworth filter that are normalized that are given to us. One is a two-pole section, that is two active elements, and one is three-pole section, that is three active elements. So this is a two-pole section, you have two active elements right here, and then you have three active elements. Reactive elements, not active, reactive elements. And with the combination of two and three pole, we can design, larger filter, 4-pole, 5-pole, 6-pole. We can cascade them together, and that's what we are going to do. Now, these normalized filters, they have cutoff frequency normalized 1 radian per second, and a gain of unity in the passband. So although they're active filters, but they're not providing any gain in the passband. The gain is unity. Input and output are going to be the same in the passband. Of course, it's going to go down a little bit because passband is until FC. FC, the gain is 70.7%. But they're not providing any extra gain in their passband. Okay, so these are the standard design. Usually when, of course, they're given to you when I ask you to design. These standard designs are given to you. And then associated with these design, as you can see, you have capacitor values C1, C2, and C1, C2, C3. Resistor values are all same. As you can see, all of them are 1 ohm. And this is your 1 ohm, 1 ohm, 1 ohm. And this resistor is your, what was that we studied in chapter number 2? Biasing the, what was that? The feedback resistor to control the biasing current. I forgot the exact name of this resistor. But we discussed in chapter 2 or chapter 3. Yeah, compensating resistor or something like that. Bias compensation resistor. Bias compensation resistor. All right, these are the values that are given in the table, which again a standard table for C1, C2 for the two-pole section, C1, C2, C3 for the three-pole section. So for the two-pole section, C1, C2 are given to you. These are the standard values in farad. So all of these are farad, and of course, it's hard to get this big of a capacitor. Of course, you'll have to change these capacitor values. And the three-pole section, C1, C2, C3. If you have to make a four-pole section, then you have to do two poles. The first two poles, C1, C2 will be this, and the second two poles, C1, C2 will be this. If you have to do fifth order circuit, then you have to do 1 3-pole and 1 2-pole. Now, it's very important that go with this table. If it says you have to put third order filter first, you got to put third order filter first. Don't put first, second order, and then third order. You're going to start with the third order. That will be followed by a second order filter. I think in the lab, you have to do a fifth order filter, I believe. In the past, I have seen some students, they were not careful about the order, and they put second order filter first and then the third order. That's not going to work. Make sure stick with what they're giving, because these are the standard values for a reason. These standard values work if you put the filters in this order to make a fifth order filter. Third goes first and then the second. And like 6 is just combination of 3, cascade of 3 two-pole filter with the specific values of C's. Remember, they are not the same values of C, they're different. And the 7th order filter is the same, first, third order, and then 2 second order filter. Observe, you can, well, there is no first order filter that we are using. Otherwise, you could have said that we can do 2 3 order and then a first order filter, but our standard is given as a 2-pole filter and a 3-pole filter. So these are our standard values, and as you can see, these values are, you cannot really find capacitors with these values. That means you will have to do impedance scaling and get to the final values of capacitor, which are the one that you use usually, 10 nanofarad, 100 nanofarad, whatever. And likewise, all the values of resistor are 1 ohm. Again, those values are not really the one that we use, so we'll have to use the impedance scaling to change these values. We're going to use one impedance scaling, and then we can change capacitor resistor, or if there are multiple sections, we can use different impedance scaling for each section to change the values. Generally, it's better just to use one value for all sections. And of course, cutoff frequency is 1 radian per second, and we'll have to change that based on our requirement. This is all we discussed. To achieve a specific value of capacitor, we will use impedance scaling, and we can use separate impedance scaling as well. So let's look at the example. Design a 5-pole active low-pass filter with 3 decibel frequency of 2 kilohertz. So this is your F of C, 2 kilohertz. I'm sorry? Say it again. All right, normalized model with the cutoff frequency of 1 radian per second is shown. So again, we're gonna put, since it's a 5th order filter, we're gonna put the 3rd order first, as you can see, followed by the 2nd order. These are 2 normalized filter, and these are the values. So this is your C1 for the first, C2 for the first, and C3 for the first. And then we can call this C1 prime for the second and C2 prime for the second. Or you can call them C4 and C5, whatever you call them. And these values are coming from the table 1.753, 1.354, 1.753, 1.354, 0.414, and 3.235 and 0.3089. 3.3235 and 0.3089. Resistors are all 1 ohms. The first thing that we are doing is we are going to find the frequency scaling factor, because we want the frequency to be 2 kilohertz or omega C to be 2 times 2, 4, so 4000 pi radian per second. So the frequency scaling factor is the new value of omega cutoff, old value of omega cutoff, or standard value of omega cutoff. So that's going to give us 4000 pi as our KF, which is 12,566. The next step is to divide either the values of capacitors or the values of resistor by this to get the intermediate values of capacitor or resistor, because we have to go and do one more time, change one more time to get the final values. So we're going to go ahead. All capacitors values will be divided by KF to get the new values that will yield the cutoff frequency of 2 kilohertz. So we divided all of these values by 12,566, and the resultant capacitor values are these. So this is C1, C2, C3, and C1 prime and C2 prime. Again, these are new values, right? So this is my second circuit, which is the intermediate circuit. It's not the final circuit. But now the cutoff frequency is set at 2 kilohertz for that circuit. If you do this circuit in PSpice, use the same values and plot your frequency response using AC sweep, then you will see at 2 kilohertz you're going to have 0.7071 of whatever input you're using. All right, let's assume that the targeted value of resistor in the first stage is 27 kilo ohm. So now I'm targeting the value of resistors. 27 kilo ohm for the first one, 22 kilo ohm in the second one. I don't know how did I target it. Maybe it was given in the book, or maybe I just chose some value, I forgot. But you can target capacitors or you can target resistors. Since the value of resistor is all 1, if we target that value, we know that we're going to change those values to whatever values we are targeting. Capacitors values are not all the same, right? So you can target one value of the capacitor. Let's say you can say, I want C1 to be 10 nanofarad. That's fine. You can calculate your impedance factor using that capacitor C1, and then divide all the capacitors by that factor and multiply all the resistor by that factor. That's perfectly fine. That's actually, I ask you most of the time, that make sure C1 value is 10 nanofarad for the first stage and C1 value of the second stage is 100 nanofarad or something. So if that is given to you, then just you target that value and calculate KF for the first stage. I mean KR for the first stage, KR for the second stage. Yes. You have to divide what? I'm sorry. Well, no, that's going to be 3. So let's just multiply that 3 times 27 or 22. Yeah. You just multiply that. So it's 3 ohms, and we are targeting 1 to be 27,000. So you just multiply that 3 times 27,000, and that's the value of that resistor in the final circuit. It does. I mean, you have to choose it accordingly because it needs to have a specific range of values in order to compensate for that current or the voltage that is developed by the current that is going inside the bias compensation current. It cannot be just any value. It has to be a range of values in general to compensate the effect. It's not a specific value, it's a range of values. Okay, so again, we are targeting resistors. So 22 kilo ohm for the first, 27 kilo ohm for the first, and 22 for the second. So for the first, we calculated the impedance scaling factor, the new value of resistor, which is 27, divided by the old value, which is 1. So it's just going to be 27. So all the values of resistor are going to be 27 kilo ohm for the first one. All the values of the resistor, second stage, are going to be 22 kilo ohm. And the factor is going to be 27 and 22K. And then we're going to go ahead and multiply all resistor. Well, we don't really multiply. Basically, it's already 27 and 22. And divide all the values of capacitor. And the final circuit is shown. I think this was in the book, so I just copied that from the book, basically. And the final values of capacitor are given here. So that's 5.17 nanofarad, 1.24 nanofarad, and then 1.12 nanofarad, 1.1. So all these values, 3.99 nanofarad. And as you can see, 27 times 3, 81 kilo ohm is your bias compensation resistor for this, and 44 kilo ohm is the bias compensation resistor for that. Now, once again, if you don't want to choose these values, and if I ask you that C1 in the final circuit should be 10 nanofarad, and C1 dash in the final circuit should be 100 nanofarad, or if I just say that both C1s should be 10 nanofarad, I mean, you can just take any value, right? And use those to calculate the impedance scaling factor, then that's what you're going to do. You're going to use for the KR1, in this case, KR1 is going to be C1 old 139.50 micro over C1 new 10 nano. That's going to be KR1, and KR2 in that case is going to be C1 old, which is 257.43 micro over 100 nano, which is C1. So whatever factor you're going to get, you're going to multiply all the resistors, which are 1 ohm for the first stage, by this factor, and divide all the capacitor from the first stage by this value. We already know C1 is going to be 10 nano. And likewise, whatever value you're going to get for KR2, multiply all the resistors in the second stage by this value, and divide all the resistors. There's only other resistor is C2, because C1 dash we already know is going to be 100 nano. So C2 24.581 is going to be divided by KR2 to get the new value. So it's the same thing. Either you go for R or you go for C. You have to change all the values. In this case, we went for R and we changed all the values. High pass Butterworth filter to the 2-pole second order third. Let's see. What we are doing here. Oh, okay. Butterworth high pass. It's not an example. I thought it's an example. So, like we had the low pass filter, the design of the standard high pass filter is given here. Basically, your resistors and your capacitors, they switch their positions. As simple as that. So that's the 2-pole resistors values, and then 3-pole resistors values, and capacitors, they switch their position. In this case, capacitor have standard values of 1 farad, and resistor values are different, and those resistor values are given in this table. Exactly the same procedure when we are doing the design. Procedure is not different. Design a 4-pole active high-pass filter with 3 decibel frequency of 8 kHz. The final value of capacitors should be 10 nanofarad because capacitors are a standard, so we want all of them to be 10 nanofarad, which is an easy value to find in our kits. So we do exactly the same thing. First, we calculate the value of the frequency scaling factor, new frequency over the old frequency. Old frequency, normalized frequency is 1 radian per second, new frequency is 16,000 pi. So this is my frequency scaling factor. Using the frequency scaling factor, I am going to divide all the values divide all the capacitors by kf to get the new values of capacitor. That will give you the cutoff frequency of 8,000 hertz. So the new value of capacitors are 19.8944 microfarad. Once again, you can either do capacitor or resistor for the intermediate stage. So in this case, we are just leaving the resistor because they are different values, and it's always easy for us to just target the one that are the same values. That's why we target resistor in the low pass, and we are targeting capacitors in the high pass. So this is our intermediate circuit with all the capacitor values changed to 19.84 microfarad, and this circuit is going to produce the frequency of 8 kHz, cutoff frequency of 8 kHz. However, our final values of capacitor need to be 10 nanofarad. So we're going to do frequency, we're going to do impedance scaling. Impedance scaling, the old value over the new value. Old value, of course, is 19.89 micro, new value is 10 nano. So this is our impedance scaling factor. And we're going to multiply the impedance scaling factor by all the resistor values and divide all the resistor capacitor values by the impedance scaling, or in other words, 10 nanofarad will be the value of all the capacitors, and you have to calculate the values of resistor by multiplying the impedance scaling factor by each value of the resistor. This will be the final circuit. And again, if you want to confirm if your values are correct, that depends on the cutoff frequency, remember. So you create your circuit in piecewise, you give an input, connect your AC supply at the input, perform the AC sweep, and then observe at 8 kHz, you should have your 70.7% of whatever value you're using for your AC sweep. If you're using 1 volt, that's going to be 0.707 at 8 kHz from this circuit, and that's what you're doing in the lab as well. So the design is very straightforward. Of course, the 2-pole and 3-pole, if you're designing, those are standard circuits. They're given to you, they're in the book, they're given to you in the quiz, in the exam, whatnot. The table is given to you. Of course, nobody is going to memorize all these values of resistor and capacitor, so tables are given to you. Whether you're doing high pass or low pass, based on that table is provided to you. All you need to know is what is the procedure, right? The first step of the procedure is, first you calculate the frequency scaling factor based upon what is the required value of the cutoff frequency. Actually, let's move back. The first thing is to find the order of the filter. That's important. So based upon the cutoff frequency and the stop band frequency that is given to you, based on their ratio, calculate the value of x, which is the x-axis of that curve, and then find what is the smallest value of n that will satisfy your order. Now choose that. If it is 3, if it is 4, it is 5, it is 6, it is 7. Of course, we don't have, beyond 7, we don't have it in the table. So whatever value that you are choosing, it has to be between 2 and 7, because the smallest filter you can do is 2-pole, and the largest from the table you can do is 7-pole. Now, of course, you can do 8 and 9 and beyond that, but we don't have in the table at least the values. So first, you have to determine the order of the filter. If order is already given to you, that makes the life very easy, of course. If order is already given to you, 3rd order, 5th order, whatnot, then you're going to do frequency scaling first. Use the frequency scaling to change the value of one of the components, either the capacitor or the resistor, I would say choose the value that is the same value. So resistor in the first one, capacitor in the second one, high pass. And then you have to target for whatever value you need for the final value. Either it's a capacitor value or resistor value, you have to target one of them, calculate the impedance scaling factor, and then scale all the values for the final one, divide all the capacitor by the impedance scaling, multiply all the resistors by the impedance scaling, and you get your final circuit done. Any question about this? Okay. I think that is the last slide. So we are done. This chapter is finished. Go ahead.